This is a tutorial on how to solve a simply supported beam which consists of 3 point loads pushing down on a beam with a pin joint and a roller joint pushing back up. So this is my beam, and what we have is we have a series of pin loads at different sections of our beam. What we have to determine to make sure everything's nice and balanced is what is our RA, this one here on our left, and what is our RB, this one here on the right. Now, just to go over some common knowledge, in the construction area, this is a known as a pin. It's a construction pin. It means it actually is physically fixed, it cannot move. We can only really pin around that joint on the end here. This side is known as a roller, and we have some terms of flexibility, either left to right or sometimes up or down depending on the construction. So what we have to do is we have to apply some values to our pins. So coming down on each three, okay, I have 125 kilonewtons, I have 100, and I have 160. They're all pushing down on my beam, and what I have to do is try and understand and balance the two sides of RA and RB, essentially what am I pushing back up on my beam. These are then put at distances, so we know that 125 is located at 2 meters, 100 is located at 4 meters, 160 is located at 6 meters. If we take a datum point from RA, so this section here, that's my datum, so I'm going to star it, which means 0 meters, all the way to RB, this section here, it's 7 meters of duration. So what I'm going to do is I'm going to start to balance my beam. So why do we need to balance? Well, this is a static system. Remember that static systems, there is no movement. Okay, so we are physically limited on a movement there. So what we mean by no movement is there's no way up or down, left or right, or actually we have clockwise and anti-clockwise, known as moments. So we need to lock out all of these together. So in the theory, what we're looking for is forces in the horizontal, forces in the vertical must equal sum of 0, and also you've got moments clockwise, moments anti-clockwise must also equal the sum of 0. So taking on those facts, what we're going to do is we need to then come up with the way of balancing both sides of our beam. Obviously on our beam we have a support A and a support B. So what we need to do is, with our loads coming down, is we need to decide how we're going to decipher which one to solve first. Most commonly in textbooks, what it would do, it gets you to put a datum point, okay, normally on the 0 mark, and it gets you to work from left to right. So what we can do, starting from A, we're going to work left to right. Okay, this will then give us our first location. So what I'm going to do is, when we're working from left to right, we know that RA sits on 0 meters. We know that then P1, okay, is at a distance away from our datum. We know that P2 is also at a secondary distance away from our datum, and in this case we know that P3 is also at a distance away from our datum. Lastly, we also know that RB or B or reaction point B, whatever you want to call it, I'm going to call in this case RB, is also at our distance. Now we know this is our length, or our beam length, so I'm going to put it as L. What we can do is then bracket all these guys up, because obviously they're individual sums. Okay, and what we have to do is all of this must equal the sum of 0. Okay, so we can't have any static tree system moving along, so essentially everything has to then be minused away to make 0. So, because we're running from 0, what we can then do is then we can start to think about, well, actually, let's try and work out from left to right, let's work out our first reaction force. So again, if I'm going to put my datum on 0, the left side of my datum then is reaction force B, which is coming up. So I'm now going to build my formula around that. So my formula is going to consist of RB times L, okay, P1 times D1, P2 times D2, P3 times D3. That's all going to equal B, so these are going to then become pluses. Out of interest, if we had a fourth, okay, you just put P4 times D4 and so on and so forth. So if you had 7, you go all the way up to P7. So you just keep adding on to that formula. I don't know what RB is, but I know it is currently 7 meters away from my datum. P1 we know is 125. Remember, this is kilonewtons, and this is set at 2 meters. We know that P2 is 100 kilonewtons, and this is set at, or times, whatever you want to do, but just put times, make it consistent. This is at 4 meters. Then we have 160 kilonewtons, and this is set at 6 meters. So what I'm going to do is just going to calculate those ones. So 125 times 10 to the 3 times 2, so 250 times 10 to the power 3. Times 10 to the 3, and lastly we have 160 times 10 to the 3 times that by 6, 960. So you notice that actually I'm keeping my powers here, so obviously when you have kilonewtons, it's going to be an N, kilonewtons, and then times meters. Obviously the overall then would be kilonewton meters. That's now my new value. So that all these are here are kilonewton meters. So obviously I need to add these guys all together. So we have 250 times 10 to the 3 plus 400 times 10 to the 3 plus 960. So this can be 1.61 times 10 to the power of 6. So obviously this is currently times 10 to the 3 kilonewtons times 10 to the 6 is mega newtons. So what you have to remember is at this stage this is still RB times 7. Okay, equals 1.61 times 10 to the 6 or mega newtons. Now I want to singular RB, so essentially I'm now going to carry the times 7 over the equals, so it'll be 1.61 over 7. So again I'm going to take my answer, divide that by 7. Okay, so divided by 7 meters. And what I'm going to say is RB, which is 230, yep, 230 kilonewtons of force pushing back up on my simply supported beam. So I'm just very quickly now just going to sketch my beam. So we know RB, which is 230 kilonewtons. 125. Okay, obviously that's at 2 meters, 4 meters, 6 meters, 7 meters, 0. So what you could do, you can actually now work this in reverse. You could then move the datum. So essentially this would be 0. Okay, and then you work then right back to left using the same formula. So what you'd have to do is then work out, obviously, then your new distances. So this would then become 1 meter. See, this would then become 3 meters, and then lastly then your 2, which would then become 5 meters, and then obviously 7 meters. So again, you can run then the same numbers. So this would then be 125, 100, 160. So again, using the same kind of context, this would be RA times 7 equals. So I'm still kind of going with that concept, P1 times D1. So this would be equal to 125 times 5 plus 100 times 3 plus 160 times 1. So, because it's I like to always double check, never rely on my brain, especially this time of the evening. So it'll be 625 times 10 to the 3. I haven't put the figures in, but I'm sort of reminding myself as I go. Obviously, as long as you're consistent and you understand where the values are coming from. 625 plus 300 plus 60, 1085. Okay, that's obviously RA times 7. Okay, and then we're going to now do RA. So we're going to take that 1087 for over 7 meters. So divide that by 7. It's going to leave you with an answer of 155 kilonewtons. So now I'm going to redraw very badly. RA, RB, so we know that's 230, 155. 160, 100, 125, 2 meters, 4 meters, 6 meters, 0, 7. So that's my beam now, perfectly balanced. Last thing I do is going to do a quick check. So what I'm going to do is I'm going to do my point load total, in this case 125 plus 100 plus 160. So that's going to give me 385. I'm just going to check that because my brain is not working this evening. 385. Obviously kilonewtons. So if I know a value that's definitely going to work, so in this case RB, so I'm going to take 385. Okay, and we're going to minus RB. I've done my maths correctly. 3 minus 230, 155. So then that sort of proves a check that I'm exactly up to where I am. And obviously if you guys are getting to this point, you think actually I want to know a known variable,